Hey guys, welcome back. This is the last video for chapter 6. We're going to be talking about simple harmonic motion. It's one of my actually favorite things to teach in chapter 6 because it relates so much to the real world, and it actually takes, these sine and cosine relationships and relates them to the world around us. So let's take a look at that. So one real world application for modeling periodic motion is looking like at the height above the ground of a particular object. And that object could be swinging, it could be a water wheel, a pendulum. We'll look at those kind of things in a minute. But it could also be like something that's varying, like the height of a tide, or maybe even like temperature, is kind of periodic throughout the day. Like it goes down, it comes back up. It's not a perfect wave, but it's the same idea. It's kind of this idea of being periodic. So we call them simple harmonic motions because there's a repetitive, unchanging cycle of values, right? So that's what we're looking at. So there's an example from the Forrester book that talks about this. So let's just take a look at it. We're told that there's a water wheel. A water wheel is like, the wheel that goes into the water and then comes back out. So as the water goes through, it turns the wheel, if you're not familiar with the water wheel. The water wheel has a radius of 7 feet. So here's, oh, and I guess I should draw that because it goes down into the water a little bit. Okay, so the radius of the wheel is 7 feet, and it's mounted so that its center is 6 feet above the water. So it's actually only 6 feet above this water. So I'll say like, okay, let's say we notice that there's a little splotch on the side of the wheel, and we watch it as it moves around this rotating wheel. So as the wheel moves, you're going to see that little red splotch move, okay? We clock the wheel as making 6 revolutions per minute. So we can use that splotch to help us. So it makes 6 revolutions per minute. And we notice that 2 seconds after we start timing, the splotch is at the top, right? So it takes 2 seconds for us to get the splotch at the top. We'll still use the angles measured in radians for this problem. So this is where if you're graphing things in your calculator, you're going to want to make sure you're in radians. But we're also going to realize that our independent variable, our x-axis, is in time, because it's really rare for us to have your watches calibrated for pi, right? So our x-axis is going to be in time, but we are still using radians. So we'll talk about how to convert for that. Okay, so we want to model the vertical height of this little splotch above the surface of the water. And we can use a trig function to do that. Okay, so first of all, remember when we write a trig function, we can do transformations on that trig function by manipulating A, B, C, and D. And actually, when I did it, I'm going to update this. When I did it, I went ahead and actually already factored that B out so that you had, and then made it minus. I prefer this version. Okay. So basically what we're going to do is just work backwards. If we can figure out what A, B, C, and D should be, then we can work our way back to the equation itself. Okay, so I feel like it's much easier to kind of work your way backwards and get those characteristics to be able to come up with the equation. Oh, and don't forget, it is an equation, so I should be saying equals. Okay, so let's go back to this problem and let's try it again. Okay, so what do we know? We're told that there's a water wheel. We know that it has a radius. I kind of started drawing it last time, but let me do a little bit better version of that drawing. So here's the water wheel. Here's the water surface because the wheel goes down in. We know that the center is 6 feet from the surface of the water, but the radius in general is 7. Okay. And let's talk about what we know. Like, for example, if the surface of the water is, because we want to do everything from the surface of the water. Let's let the surface of the water be like 0, because, right, if you were on the surface, then we would say that the distance from the surface is 0. So what is the highest point that we go above the surface of the water? Well, I would go this 6, right? Because remember, you're not including that part. I would go this 6 feet plus that additional radius of 7. So the highest that I ever end up going is 13. What's the lowest we go compared to the surface of the water? Well, I would go my full radius under here, but since I'm 6 feet above, that means I would only go down 1 below the water. So we're going to call that lowest point -1, where negative will be under the water, into the water. Okay, what else do we know? We know the time it takes to make 1 revolution, right? We know technically, we know that there's 6 revolutions per 1 minute. but we want to do everything in seconds because that's what we're timing in. So we can convert this to seconds. So let's change from minutes to seconds. So that means, oh, now we can see easily that there's 6 revs per 60 seconds, or that reduces to 1 revolution per 10 seconds. This is the important part. We don't need the actual angular velocity. We need to know how long it takes to go 1 revolution. Why? What is 1 revolution when we're talking about a periodic function? Each revolution is 1 period. So this means I now know the period, how long it takes to recycle itself. Okay, and then this last part is telling us how long it takes for the splotch to get to the top. So this is like our phase shift, guys. Like normally, remember, like a cosine graph, for example, would start at the top and work its way back out, but we don't start at the top. Our graph isn't at the top. We're not at the top of our water wheel until like 2 seconds. So what would this be if you had to move your graph over so that it actually started at the top at 2 seconds? That would be affecting what? The phase shift. Okay. So we're starting to get a feel for what's happening. And then we're going to look at when the splotch kind of reaches this high point again and again. Okay. So let's look at a graph. So I'm going to scroll down through a little of this, and we're going to kind of start to plot what's happening. So the first thing that I would do is just plot that first piece of information you know. You know that after 2 seconds, so this will be in seconds, you know that after 2 seconds, you are at the top of the wheel. And the top of the wheel, we said, was 13 above the water. So let's put a little dot there. Okay. We also know that each revolution is 10 seconds. So that means the full period would be 10, which means if I add 10, I get 12. I should be all the way back at the top of the water wheel. So there's the beginning and ending of my period. And because I know this is a simple harmonic problem, it's going around in this up and down, I know that it's modeling as a sine or a cosine graph, and I'll decide that in a minute. So what I know is that it's going to reach its lowest, which we already said was -1. So see how I'm kind of creating that? It should reach its lowest halfway between. Well, if the period's 10, halfway would be if I go 5, so 7, that would be when it's at its lowest. Okay. And then we probably need that equilibrium, right? We want that halfway, because if I'm going to write the equation, I need A, B, C, and D, guys. And so I need equilibrium. So let's get equilibrium. The halfway point between -1 and 3 would be the average of those, which is 6, which makes sense. That's where the center of the wheel is. And so the center of my wheel, if I wanted to do a sketch, I could put those 2 points in halfway between the highs and lows, and then I could connect. And there's a nice sketch for me. So we know that D, the equilibrium, is now 6. We know that A, the amplitude, makes sense. It's the radius of the wheel. We need B. Well, remember, the way that we get B is by doing 2 pi over our period. So this case, it's 2 pi over, my period was 10 seconds. So that's going to reduce to pi over 5. So my B value is pi over 5. And my phase shift, I shifted over to, as long as I write it as who? Who starts at the top of the wave again? Positive cosine. So then I'm ready to write the equation. So the equation of my graph, and I'm going to use d of t for distance over time, because I'm doing distance from the top of the water. So then I can just start writing 7 cos pi over 5 t minus 2 plus 6. Boom. So now here's the cool thing, and I'm going to take out my calculator so that you can see this graph. We're gonna look at various things, like what if I want to know, because this is where you're gonna go basically with these questions. Like, what if I want to know, what's my height at, maybe 2.5 seconds? Like, what's my height there? Let's do the height at 3.7 seconds, right? Something weird. And then we're even going to take this a little step further, and we're going to say like something like find the first time that little splotch is at a height of maybe 11 feet. So that's going to be my last question. So these are kind of the different things. So here we go. We got the equation. So now I need to get that calculator out. And I'm going to put this in. So let's look. So I'm going to go to my y equals, oh, I need to make sure I'm in radians, which my calculator always starts in radians when I open it, so that's good. I'm going to get rid of that, and I'm going to put this in. So 7 cos, I've got pi over 5. Make sure you then use your parentheses to do your phase shift. So instead of a t, I'm going to use x minus 2. Close that, close the big one, right? You're going to have to close it twice when you have that phase shift, and then plus 6. Now, if I just graph this, this may or may not show up in my graph, right? Like if I just hit graph, I mean, I can kind of see it, but I can't see the top, right? So you're going to need to make good choices as far as what your window looks like. So everybody go to that window. So you should be graphing this with me. So pause it and graph it if you haven't. So go to your window, and we're going to choose what to make our x and y axis. Now, here's a smart move. Go back up to your little sketch. This is why sketching the graph is really important. Let's go to our graph. We're going to use that to help us make good choices. So our x-axis, our period is like, it's 10 seconds. And so maybe we go from x equals 0, which is when we start timing. Or maybe if you want to see the x-axis, we could say like -5. That way we can see everything. But then maybe let's do a couple periods. So maybe go to like 20. Let's do that. So let's go to x equals 20. So that'll be the first 20 seconds. Scale, you don't have to worry about. My y-axis, well, I definitely need to go lower than -1. So I'm going to say like -5. You could, -2 would work. And then I need to be able to go bigger than 13. So maybe we go up to 15. Again, you could go up to 20 if you wanted. If these are correct and you put in the correct equation, you should see the graph fit beautifully in there now. See? So now it has the x and y axis working nicely. Okay, so there's our graph. Okay, so now that we have the graph in there, we're going to plug in these values. So if I want to know a specific x or t value, that's the easiest. You literally can go to second calc, and it's that first choice. Again, I went to second calculate, and it was that first choice value. And it lets me plug in a value. So I can literally type in 2.5, and it'll give me the point when my equation, see, it's way up here. So the height was 12.657. Okay, feet. Then I can do it again. I'm going to do second calc value and 3.7. Boom. Now the height, notice it's moved down, is 9.372. We usually take them out to 3 decimal places. So there we go. Also, just so you guys know, if you are just in your graph, if you just start typing, like if I typed in 10, oops, I lied. Let me go back to that. Typically it does, but I must not be. Try this again. Usually, oh, I guess it's not going to work. I guess maybe you have to hit trace. If you hit trace, and then you can type in the number. So I could hit trace and type in 10, and it'll do that value. So you can also just hit trace instead of going through the whole second calc thing, but that's another option. So there it is at 10 seconds. Now for the second one, the second type of question, find the first time that it's at a height of 11. This is when you want to know this. Let's go back up to our sketch. You want to know when your graph, and remember, my graph actually goes backwards. Whoa, holy moly. My graph actually goes backwards too. So I have to think about that. Like it's going to go like this, right? So I want to know the first time that my height of my splotch is 11. So this is what I'm looking for, like that first time. And I think it's going to be here, but who knows? This could come back up. So this is just a horizontal line, guys. That's what we're going to put into our calculator. So to graph a horizontal line, you just do y equals that number. So I'm literally going to say y equals 11, and I'm going to graph it. And it's, oh yeah, it's going to show me where my graph is 11. It's 11 a lot of times because it's cyclical. So if I want to find this, I have to do the intersection of these two graphs. So how do I do that? Back to your old friend, second calc. So I'm going to go back into second calc. I want to intersect my graph, so I'm going to go down and choose 5. And then it'll say first curve, second curve. And if you hit up and down, it switches between, because like if I had like 5 graphs, then I would have to choose which ones to intersect. If you only have 2 graphs graphed, if you hit enter, it'll choose the first curve and it'll automatically choose the second curve. But this will tell you which one you're picking. So as long as you only have 2, you're fine. But here's the problem. If I do it over here, it's going to pick the closest, and then it says guess, and you have to say yes, so you have to hit enter again. It's going to pick the closest intersection, which for me is way over here. Well, I don't want that intersection. I want the first one. So how do I make sure that it finds the first one? Well, let's go back to second calc. Let's say intersect, and you're going to move closest to that. So like I actually like to move on the horizontal line, so I clicked up so that I could move on this graph. So I'm going to click over, and I'm going to get closest to the intersection I want to find. Then I'm going to say first curve, yes. So I had to move to the closest intersection that I wanted. Second curve, yes. Remember, it asked you to guess just to make sure. You'll hit yes. There you go. So the first time that my graph was at a height of 11 was at 0.766 seconds. Okay? Okay. That's basically it, guys. I can look at one more real quick just to show you another example. Like maybe we were talking, maybe temperature. For some reason, temperature was periodic. So they would tell you something like that. And usually they say it like this. They say something like, temperature varies sinusoidally with time. That means like a perfect sine / cosine graph. That's what a sinusoid is, cosine. So temperature varies sinusoidally with time. Maybe you start watching at like midnight, and maybe on, let's see, what's today? Midnight on 10/6, and maybe at midnight, maybe you notice that at 2 a.m., well, I won't use 2 because I just did one with 2. Let's say that you notice that at 3:30 a.m., your temperature is 38 degrees Fahrenheit. And then maybe you notice, and this is its lowest temperature that it's going to reach. That's important. And then maybe at, I don't know, let's say at 2:15 p.m., it's at its highest, which is maybe 50 degrees. Okay. And we're going to want to model. So we want to model this as a function of temperature and time. So the first thing that we want to do is model this. Then we're gonna sketch a graph. So we actually might do the sketch first and then the model. And then I'm going to say something like, okay, I want to know the temperature when, or wait, yeah, I want to know the temperature at maybe, how about 10:10 a.m. on 10/6. And then maybe I also want to know the temperature at, how about, let's do 5 p.m. on 10/7. Ooh, that's tricky. And then my last one, when is the second time the temperature is 48 degrees Fahrenheit since midnight? Okay. Whew. All right, lots going on. Okay, so the first thing that I would do with this is I would start with a sketch. So I actually start with the second thing. So I'm going to do the sketch first. So the first thing I know, and I would mark, is that this is midnight and it's on 10/6. It's also time equals 0. So we've kind of got a lot of stuff going on. We've got 0, we've got the clock time, and then we've got the date. That's when time starts. Then we know at 3:30, which 3:30 a.m. is actually what time on the x-axis, because you can't put 3:30. You would say 3 hours and a half, so 3.5, still 10/6. That's when it's its lowest, which is 38 degrees. So this is just a sketch, so our axis doesn't have to be perfect. Then they said if you go to 2:15 p.m., so 2:15 p.m., careful, 2:15 p.m. would actually be how many hours since midnight? Let's think about this. Midnight to noon would be 12 hours plus an additional 2.25. So that would be a total of 14.25, right? I want everybody to see that because I had to go the 12 to get to noon and then the additional. Okay, so this is what it would be on the x-axis, and that's when it's at its high, which is 50 degrees. So now, is this a full period if I go from low to high? No, I have to go back down to low. So I would have to go another, let's see, how much is this in between here? Between 3.5 and 14.25, and you can just subtract those. I mean, you could use a calculator. So I get that this distance is 10.75. So I got to go another 10.75. So if I do that, that gives me 25 on the x-axis, but think about what 25 means. 25 hours would be 1 a.m. on the 7th. So like here is like 24 hours, which is like my first day. Okay, and then it's back to the low. So there, I went the full cycle. Whee! Okay, I probably need my equilibrium, so I'm going to find the average of 50 and 38. And I get 44. And then I need to write my model. So if I want to write my model, this is when I need like, this is when I need like A, B, C, and D. So let's see what we can get. I would start with D. Your equilibrium is at 44. Your amplitude is just your distance here, so 6. Your B value, well, my B value is found by doing 2 pi over the period. So how much was the period? Well, the period goes from, careful, low all the way to that low. So from here to here, let's figure out, we can just do 25 minus 3.5. So I got 21.5. So this is my B value. I really can't reduce that. If I don't like the fact that that has a decimal, I could multiply the top and bottom by 2 and use like 43, but this is fine. So what a nasty B value, but totally fine. That's what it is. And then C, well, just start wherever your graph starts. So my graph started at 3.5 seconds and it's to the right. So I'm going to use 3.5. But because it's starting at a low, guys, which graph starts at its low? Negative cos. That's right. So I'm going to have to write this as a negative cosine. Okay, so let's try it. So my model, so I'll start with the model. I'm going to scooch down. So my model is big T, big temperature of time was -6. Remember, because it started at the bottom. Cosine. My B value is going to be here. T minus 3.5. I shifted 3.5 to the right. And then plus 44. Whew, that is a nasty equation, which is why everything else is done in your calculator. So let's put that guy into the calculator. So do it with me. So I'm going to go back and clear everything else out. And I'm going to say, make sure you use your negative symbol. I've got 2 pi over 21.5. You need your extra parenthesis for your phase shift. Close off both, and then plus 44. Now, if you hit graph, it's probably not going to be very nice because your window is not set up for this graph, right? We might not even see anything, to be honest. So don't freak out. You got to change your window. So let's go to window. My x-axis, I should probably go all the way through at least 25 so that I can at least see a full day. And for my y-axis, I really only need to go a little under 38. So I'm going to go from 35 and then up past 50, so maybe to 55. Sounds good. Oops, not 535. Okay, there we go. Now, when I hit graph, it should work. If it doesn't, I've typed something in wrong. Oh, nope, there it showed up. So there's my graph. Yay. And if we wanted to see more, we could just make our x-axis go longer. Okay, so let's try these questions let's try these questions that are asked. So the first one is, what is the temperature at 10:10? Well, we have to figure out what 10:10 is. Obviously, it's 10 hours, but you got to figure out the decimal. So 10 minutes would be, I'm doing 3. 10 minutes would be 10 out of 60. So I'm going to have to plug in 10 plus 10 over 60, but I can do that. So I'm going to go second calc value. And I'm going to say 10 plus 10 over 60, right? You don't have to worry about making, unless the fraction is nice, which 1/6 isn't nice to write, so that's why I'm doing it like this. So this is going to find when the time is 10 and 10/60ths. So there we go. So my temperature is 46.211 degrees. Let's do it for 5 p.m. But this one wants 5 p.m. on the 7th. Holy moly. Okay. Remember that we're starting from midnight. So if I want to go, first of all, just to get to 10/7, I have to go 24 hours. Then I got to go to 5 p.m. So let's think about that. So that would be 24 full hours, plus you got to go all the way to 5 p.m. So that would be plus 12 to get you to noon, plus another 5. So that gets me to what? What is that? 36 plus 5, 41. So this is a total of time being 41 because I have to go to 5 p.m. on the 7th. Now here's the problem. If you try to plug in 41, you're going to get an error. My calculator just shut down. It was that mad at me. It even got, oh my God, it really hated me. It even got rid of the thing. The reason that it freaked out is because my window wasn't big enough to go to 41. I think I only went to like 25. So let me put everything, I did not know, it doesn't normally shut down on people. I didn't know it was going to do that. So let me put my window back. So my x-axis then has to go all the way to at least to the number I'm going to plug in. So if I'm going to plug in 41, then I need to at least make sure that my graph will go to 41. So my calculator is being very difficult right now. Hold on. Okay, so I'm going to say instead of 41, maybe if I make it go to 50, it'll definitely be big enough. And you shouldn't have to change these. I just have to because my calculator started over. Okay, so there we go. Oh, there we go. So now we should be able to plug in time equals 41 hours. So now let's do that. Second calc, value, 41 hours. That's 5 p.m. So there we go. So at 5 p.m., it's 44.219 degrees. So at 5 p.m. on 10/7, the temperature was, whoops, what did I say? 44.219 degrees. All right, we're almost done. Hang with me. Last piece for number 4 is, when is the second time that the temperature is 48 since midnight? Okay, so let's look at our graph. 48 degrees is going to be somewhere up here. Now, it may hit back here. We don't know, but remember, we want the second time. So we need to graph the line y equals 48, that horizontal line. So let's do it. Okay, and let's look at the graph again. So there we go. So I want the second time. So there, you can see right there is my second time when it hits it. So I'm going to do intersect, second calc, intersect. I'm going to make sure that I move close to that little intersection. Oops. There we go. Doesn't have to be right on it, but it has to be the closest one. Okay, and then I'm going to do enter, 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 right? Second, first, second, and guess. So that the second time it's 48 after midnight, which is this 0, is 17.128. So this last one is at time equals 17.128. Now, if you want to get more technical, 17 hours, right? If you wanted to put it into like the clock. So I would take away 12 because that would be getting me to noon. So this is going to be at 5 p.m. because I can tell. And then I have to change 0.128 into minutes. I could do that too. So that's going to be, let's see, 0.128 of a minute. There we go. So this is about 5:08. So about 5:08 p.m. Now this was a hard one because I gave you the dates and all that, but the general setup of these are not too bad. So you're going to get a chance to practice these and play around with them in the Forster 2 packet. They're pretty fun. I think you'll enjoy them. Make sure that you're doing that sketch. Make sure that you're changing that window when you need to, and good luck with it. I'll see you in class.